this example, we have a 25-watt heating element that's heating up 10 grams of water, and within 60 seconds it raises the temperature from 20 degrees Celsius to 50 degrees Celsius. And you're asked to calculate the efficiency of this process. So again, let's think of this problem in terms of input over output. So we have our input, which is 25 watt of, in terms of electrical energy, and then we have our output is enthalpy change in water. So this is a classic thermodynamic example where you're using electrical energy and the resulting output is enthalpy change. So we draw an arrow. So the question is, what's the efficiency of this process? So one thing we have to do is to convert both input and output in same units. So enthalpy change is, you can predict, will be in joules, and power is in watts. So for this problem, I think it will be best to convert everything in joules. So we'll convert our common unit will be joules. So power is simply, energy here is simply power times time. So we know our power is 25 watt and our time is 60 seconds. That turns out to be 1500 joules. Enthalpy change, delta H, is the product of three variables. One is the mass of water, the specific heat of water, times delta temperature, change in temperature. So we know the mass of water is 10 grams. The specific heat capacity that's given is 4.184 joules per gram Kelvin. And then change in temperature is 50 minus 20 degrees C. So if we multiply all these numbers, this turns out to be 1255 joules. So now, again, you've seen this equation plenty of times before. Efficiency is simply output over input. So the output in this case is change in enthalpy of water, which we computed to be 1255 joules. Our input is the electrical energy supplied by the heating element. That's 1500 joules times 100. That number turns out to be 83.7%. So a couple of questions we might ask. So you start with 1500 joules of energy, and as you supply that energy to water, the enthalpy change in water is only 1255. So where does the difference go? So let's compute the difference first. So the difference between input and output is equal to 1500 minus 1255. So 245 joules of energy is simply gone somewhere. By conserving enough energy, that energy can't just simply disappear. So what happened is one of the key elements you notice in the example is it's not insulated. So that's a hint right there. So as the water gets heated up from 20 degrees to 50 degrees, we can assume in this case that surrounding temperature, the room temperature, is around 20 degrees Celsius. So some of this heat energy is lost to the surroundings. So this energy lost to surroundings. So if you wanted to develop a more efficient heating device, you will put insulation to improve efficiency. Okay.